The world of computing is on the brink of a revolution fueled by the enigmatic principles of quantum mechanics. At the forefront of this revolution stands Microsoft, a company that has been diligently working towards building a scalable and reliable quantum computer. Their latest breakthrough, the Majorana 1 chip, marks a significant leap forward in the field, promising to unlock unprecedented computational power. Microsoft's journey into the quantum realm has been marked by a steady pursuit of topological qubits, a unique approach that leverages the bizarre but predictable behavior of Majorana particles. This pursuit stems from the understanding that traditional qubit designs, while promising, are inherently fragile and susceptible to errors. The Majorana 1 chip, with its innovative architecture and integration of hardware and control electronics, represents a culmination of years of research and development. It stands as a testament to Microsoft's commitment to tackling the fundamental challenges of quantum computing, paving the way for a future where complex scientific problems, once deemed unsolvable, could be unraveled with unparalleled speed and precision. This is not just about building a faster computer, it's about unlocking new frontiers in medicine, material science, artificial intelligence, and countless other fields. The implications of Microsoft's breakthrough are far-reaching, promising to reshape our understanding of the world and propel us into a new era of technological advancement. In the heart of a quantum computer lies the qubit, the quantum equivalent of a classical bit. Unlike classical bits, which can exist as either a 0 or a 1, qubits can exist in a superposition, simultaneously representing both states. This unique property, along with the quantum phenomena of entanglement, allows quantum computers to perform calculations that are impossible for even the most powerful classical computers. These calculations can solve complex problems in seconds that would take classical computers millennia. However, the very nature that gives qubits their power also makes them incredibly delicate. Qubits are extremely sensitive to their environment, and even the slightest disturbance can cause them to lose their quantum state, a phenomenon known as decoherence. This susceptibility to errors has been a major obstacle in the development of reliable quantum computers. Researchers have been tirelessly working to find solutions to this problem. This is where topological qubits, the foundation of Microsoft's approach, come into play. Unlike traditional qubits, which are often based on individual atoms or ions, topological qubits are built upon the collective behavior of many electrons. This collective behavior gives rise to a special kind of protection, making them inherently more resistant to noise and errors. This resistance is crucial for the stability and reliability of quantum computations. Imagine a braid, its strands interwoven in a complex pattern. Even if you tug or pull at individual strands, the overall structure of the braid remains intact. This is analogous to the robustness of topological qubits. The information they encode is not stored in a single, fragile location, but is distributed across the entire system, making them incredibly resilient to external disturbances. This resilience is what makes topological qubits a promising candidate for the future of quantum computing. To understand the magic behind topological qubits, we must delve into the realm of Majorana particles, elusive entities that hold the key to Microsoft's quantum breakthrough. These particles, named after the Italian physicist Ettore Majorana, are not your everyday particles like electrons or protons. They belong to a special class of particles known as Majorana fermions, predicted to be their own antiparticles. The concept of a particle being its own antiparticle might seem strange, but in the quantum world, strangeness is the norm. When a Majorana particle collides with its antiparticle, which is itself, they annihilate each other, releasing energy. This self-annihilating nature is a key characteristic that makes Majorana particles so intriguing for quantum computing. You see, Majorana particles are not found freely in nature. Instead, they emerge as quasi-particles, collective excitations that behave like particles in certain exotic materials. Think of it like a ripple in a pond. The ripple itself isn't a separate entity, but arises from the collective movement of water molecules. The challenge lies in creating the right conditions for these elusive Majorana particles to emerge and, more importantly, controlling their behavior. This is where topoconductors, the special materials used in Microsoft's Majorana 1 chip, come into play. Section 4. Topoconductors, the architects of stability. Topoconductors, as their name suggests, are materials that exhibit both topological properties and conductivity. In simpler terms, they are like highways for electrons, but with a twist. In these materials, electrons can flow freely on the surface, but their movement is governed by the material's unique topology. Imagine a highway with lanes that twist and turn in specific ways. Even if there are bumps or obstacles on the road, the cars are guided along these predetermined paths, ensuring smooth and uninterrupted flow. This is akin to how topoconductors protect the flow of electrons on their surface, making them resistant to imperfections or disturbances. Now here's where the magic happens. When a topoconductor is combined with a superconductor, a material that allows electricity to flow with zero resistance, something extraordinary occurs at their interface. Under the right conditions, Majorana particles emerge as quasi-particles bound to defects or edges of the material. These Majorana particles, once elusive and theoretical, become tangible entities, their behavior governed by the robust topological properties of the topoconductor. This is the foundation of Microsoft's approach to building stable and error-resistant qubits. Section 5. Scaling New Heights, a Million Qubit Future. One of the most significant advantages of Microsoft's topological qubit approach is its potential for scalability. This approach is not just about adding more qubits, it's about ensuring that each additional qubit enhances the system's overall performance and reliability. Building a quantum computer with a few qubits is one thing, but scaling it up to hundreds, thousands, or even millions of qubits is a challenge of a different magnitude. Each step in scaling introduces new complexities and potential points of failure. This is where the robustness of topological qubits, combined with Microsoft's innovative chip architecture, truly shines. These qubits are designed to be more stable and less prone to errors, making them ideal for large-scale quantum computing. Traditional qubit designs often face limitations when it comes to scaling. These limitations can significantly hinder the development of practical, large-scale quantum computers. The more qubits you pack together, the harder it becomes to control them individually and protect them from errors. This is a major hurdle in the path to achieving a million-qubit quantum computer. Imagine trying to orchestrate a symphony orchestra where each musician is incredibly sensitive to the slightest sound or movement. The complexity is immense and the need for precision is paramount. Microsoft's approach, however, offers a more scalable path. By focusing on topological qubits, they aim to simplify the control and error correction processes. The Majorana 1 chip is designed with scalability in mind, allowing for the integration of a large number of qubits on a single chip. This design is a significant step forward in the quest for a million-qubit quantum computer. The company claims that their architecture could potentially lead to quantum computers with 1 million or more qubits, a scale that was previously unimaginable. This would revolutionize the field of quantum computing. This scalability is a game-changer. It opens up new avenues for research and application that were once thought to be out of reach. It opens up the possibility of tackling problems that are currently intractable for even the most powerful supercomputers. Problems that require immense computational power and precision. Imagine simulating complex molecules to design new drugs and materials, with a level of detail and accuracy that was previously unattainable. Optimizing logistics and financial models with unprecedented accuracy, leading to more efficient and cost-effective solutions. Or breaking the encryption codes that protect our most sensitive data. The possibilities are limitless, and the future of quantum computing looks incredibly promising. Section 6. A symphony of hardware and software. The Majorana 1 chip is not just about the qubits, it's about the seamless integration of hardware and control electronics. This integration is what makes the chip so powerful and unique in the realm of quantum computing. Building a quantum computer is like orchestrating a complex symphony, where the qubits are the instruments and the control electronics are the conductor, guiding their every move. Each component must work in perfect harmony to achieve the desired outcome. Microsoft has developed a sophisticated system that allows them to manipulate and measure the state of their topological qubits with remarkable precision. This precision is crucial for the stability and reliability of quantum computations. This involves generating precise microwave pulses to control the Majorana particles, ensuring that they behave in a predictable and controllable manner, as well as using sensitive detectors to read out the qubit's states. These detectors are finely tuned to capture even the slightest changes in the qubit's states. What sets Microsoft's approach apart is the tight integration of these control electronics directly on the chip with the qubits. This on-chip integration is a game changer in the field. This minimizes the signal loss and interference that can occur when the control electronics are located off-chip, as is often the case with other designs. Reducing signal loss is essential for maintaining the integrity of quantum information. This tight integration is crucial for achieving the high level of control and fidelity required for complex quantum computations. Without it, the accuracy of quantum operations would be compromised. Furthermore, Microsoft has developed a comprehensive software stack that makes it easier for developers to write and run quantum algorithms. This software stack is designed to be user-friendly and highly efficient. This includes high-level programming languages that abstract away the complexities of quantum computing, allowing developers to focus on solving problems rather than dealing with the intricacies of quantum mechanics, as well as tools for simulating and debugging quantum circuits. These tools are essential for ensuring that quantum algorithms run correctly and efficiently. This focus on software, alongside hardware advancements, is essential for making quantum computing more accessible and practical for a wider range of applications. By bridging the gap between hardware and software, Microsoft is paving the way for the future of quantum technology.